Yeah, welcome back everyone. So since you're working so hard and I've heard a lot of other stuff, I just try to summarize what we arrived at. Yeah, besides the fact that dark matter exists and we have to explain it, and the one number that we know about is the cosmological density. Yeah, so I wanted to organize everything with respect to production mechanisms. And in order to do so, we started to discuss the Boltzmann equation. Yeah, this is a covariant definition. I briefly flashed how to calculate this in Friedman, Robertson, Walker background, and that's what you're supposed to do after the lecture in more detail. This is the result, and one of the important take-homes from this, which can lead to some confusion, is that in the process you also learn what this P actually is. Yeah, and if you state the Liouville operator in this form, the P is the physical, what's referred to as the physical momentum, so the momentum that a freely falling observer measures. Yeah, you can express, of course, the Liouville operator in any other frame. Yeah, for example, in terms of co-moving momenta. In terms of co-moving momenta, it's just the time derivative. Yeah, so you really have to make sure to state what the P is. Yeah, so that means the P in this form is the standard P that you would need and use in your classical physics, QFT, whatever. Yeah, which is also important in order to know how to write down the collision operator. Yeah, so this is the standard Lorentz invariant P of an ordinary observer that we're using. Okay, so then the Boltzmann equation simply states that the Liouville operator should be the same as the collision operator. So in the absence of any collisions, it's just the Liouville operator being 0. Yeah, and then I said that, well, I mean, this is basically an equation for the phase space density at the phase space level. Yeah, so it's a partial differential equation, which is not that easy to solve. But typically it's sufficient to consider like moments of this equation. And the thing that we started with is the first moment or 0th moment, depending on how you count, by integrating out all the momenta. Yeah, and that gives you the Boltzmann equation at the number density level. Yeah, so concretely, if we perform this operation here on the left-hand side, yeah, the leading moment of the Liouville operator, we calculate it to be this one. Yeah, and the interpretation is, so n is the number density now, not the phase space density anymore, and the interpretation is easier to see in this way of rewriting it, namely that it's the time derivative of the co-moving number density. So if there are no collisions, 0 on the right-hand side, this just means that the co-moving number density is conserved, which is of course what you would expect. Right? Okay, and then next we want to study the collision operator in some more detail. You've actually seen this form in Yvonne's lecture notes. Let me just rephrase this also to introduce my own conventions here. Yeah, so this is specializing to the case of a 2-to-2 interaction. And then the collision operator is of this form. Yeah, so just to restate where this comes from or why it takes this form. So here, I mean, if you look at this first, yeah, so this is the amplitude. So for the process to happen in this way, the amplitude squared, so the probability density, and you multiply this with the number densities or phase space densities of the incoming particles. Yeah, so that just means that, well, the rate for this process to happen is clearly, well, the number densities, the number of particles that you have to participate, times the probability for the process to happen. Yeah, and then what's happening here is that you simply sum over all possible configuration that are allowed. Yeah, remember that these things here are Lorentz invariant measures, so you sum over all possible phase space configurations, including those that satisfy, or only taking into account those that satisfy energy momentum conservation. Yeah, so that's essentially a classical expression, yeah, using a quantum mechanical form or way of calculating the amplitude, but fundamentally the way we state the Boltzmann equation or the collision operator is actually a classical form. And we just use quantum mechanics to calculate the probability. Then there are these correction factors to that. And these are intrinsically quantum mechanical effects, yeah, stating that when you have this process here, yeah, 2 particles going into these 2 particles, then the rate is actually not only proportional to the number densities of the initial state, but it also matters what you have in the final state. Yeah, so at the classical level, you would expect these yellow boxes to be just 1, but there are quantum mechanical corrections depending on whether you have bosons or fermions. Yeah, so you know this effect from quantum mechanics. There's something like stimulated emission. If you have bosons, that's what happens in a laser, for example. That's when the plus sign appears. So if you have a high occupation number in the final state, yeah, you actually preferentially annihilate or react into that state, while for fermions there's a minus sign because of Pauli blocking. This is sort of how to intuitively understand where this comes from. Okay. And then, as I said, I mean, for many applications we're just interested in this simplified Boltzmann equation at the number density level. So now we want to basically calculate this collision term here in this simplified version. So we integrate over all momenta. And then the basically most important applications that we have of this kind of 2-to-2 process is, in the context that we're discussing here, is dark matter scattering on heat bath particles, or dark matter annihilating into heat bath particles, or the opposite, heat bath particles creating a pair of dark matter particles. Yeah, so let's start with a case of dark matter scattering. So that means that our particle number 3 here is also a dark matter particle, and 1 and 2 are standard model, or in general heat bath particles. Yeah, so in what follows, because I don't always want to write this out, I will often call the dark matter particle chi, and these heat bath particles or standard model particles psi. Okay, and then the result is very simple. Yeah, you can actually already guess that. Yeah, so if you have a dark matter particle here and a dark matter particle there, yeah, this is supposed to give us the change in the number density. Yeah, so this should be 0. Yeah, and one of the things you should check this afternoon is that it's actually 0. Yeah, starting from this expression, just to get some familiarity with these kind of phase space integrals. Okay, so then we have dark matter pair annihilation or creation. Annihilation, creation. Yeah, so there we have basically, we want to study the case that this one here is also dark matter, but on top of that we want to require the dark matter particle to be non-relativistic. Yeah, and yes? Okay, so I gave you an intuitive argument, yeah, and that is because if you have scattering, it means you have standard model, dark matter. So both in this direction and in this direction, you do not change the number of dark matter particles. Yeah, but this is just sort of your physics expectation. But then, of course, you can like algebraically just check that the statement is correct, and that's left for you for the afternoon. Yeah, it's not difficult. Okay, so why do I focus on non-relativistic chi's here, dark matter particles? Basically because of our introduction. Yeah, so we know that dark matter should be non-relativistic. If it's hot, then it doesn't match observations. Yeah, it wouldn't lead to the kind of structure that we observe in the universe. Okay, so then particles 2 and 3, 2 and 3, K2 and K3 are heat bath particles. Okay, so what does that mean to be a heat bath particle? It means that these particles are in thermal equilibrium. Yeah, so they form a plasma. So that means that we actually know their phase space densities. Yeah, they follow the equilibrium distributions. And you also learned in Yvonne's lecture that for standard model particles we can safely neglect chemical potentials here, just because annihilations are so efficient, in particular into photons, which don't carry chemical potentials. Okay. And then, well, you can start with these, with this here as a starting point. You integrate over the momenta, and then you basically just need a few assumptions here, well motivated assumptions. So one is basically CP invariance. Yeah, so that is that the matrix element squared in this direction is the same as in this for annihilation and creation. You need to formally assume detailed balance, meaning that in equilibrium, the rate in this direction must be the same as this. Yeah? So if all these f's here are equilibrium distributions, not only the f psi's, also the dark matter f's, then this rate must be the same as this. Yeah, that's detailed balance. And basically because otherwise you wouldn't be in equilibrium if you wouldn't create and annihilate particles at the same rate. And finally, you can make an assumption on ansatz for the dark matter density, phase space density of this form. So why is that? Yeah, this is the strongest physics assumption. This is basically stating that even though, we want to describe the change in the number density of dark matter particles, so we don't have full thermodynamic equilibrium, but still we are in kinetic equilibrium. So that means that dark matter particles are scattering very efficiently on the heat bath particles, so they have a well-defined velocity distribution, a Maxwellian velocity distribution, as in thermal equilibrium. And then I leave it again as an exercise for the afternoon. That means that, well, the left-hand side of the Boltzmann equation we know already, but for the right-hand side, you find the following expression. Yeah, which most of you will have seen before as being quoted as the Boltzmann equation. Yeah, so just to make the point again, the actual Boltzmann equation is this one at the phase space level, and you have to actually make a couple of assumptions in order to arrive at this equation, which is typically as a standard used in the dark matter context to calculate the relic density. Okay, so what are the symbols that are introduced here? Sigma V is the thermally averaged value of the product of the cross-section times the relative velocity of the particles. And it's actually important there that you choose the right definition of relative velocity. Yeah, it's the so-called Möller velocity. It's again one of these things that you will explore in detail in the exercises. So I just state this here. Sigma V. Yeah, so by thermal average, we simply mean that we integrate over the phase space distributions. Okay, and one of the simplest way of seeing that you actually need the Möller velocity, and that, for example, if you just use the center of mass relative velocity instead, that this fails, is to assume that, for example, sigma v, if that is a constant, but you use the center of mass velocity here, then you will not get the same constant in the thermal average. So it's a nice exercise. Okay, so then it turns out that you can actually perform these integrals. Yeah, these are 6 phase space integrals, and you can perform 5 of them. And you can restate this in the following way. So let me first write this down, and then I define the symbols. Yeah, so now I don't need explicitly this velocity anymore, it's only the cross-section that enters. Here, S is basically a dimensionless version of the Mandelstam variable S. So we divide by 4 times the dark matter mass squared. Yeah, so in the limit of extremely small velocities, this becomes 1, which is why the integral starts at 1. And X is a dimensionless version of the temperature, or the inverse temperature. Yeah, so you can think of this as a time parameter. So as the universe expands, cools down, X increases. Okay, so let's discuss this equation here. Maybe I'll start. There was a question? No. Okay, so in order to discuss this equation here, yeah, we need to also understand what this NEQ is. Oh, sorry, I should mention that, okay, so the K's are Bessel functions. Yeah, K1 and K2. Okay, so the NEQ, what is that? That's the number density the particles, the dark matter particles would have in some equilibrium. Yeah, so if we make the same assumption as this one, well, actually like this, because we are in the non-relativistic case, so we can neglect the plus minus 1. So we have a Boltzmann distribution, but with a factor of proportionality that is just 1. Yeah, you integrate over this, you get the number density, that's the NEQ. Okay, and then you actually also know from Yvonne's lectures how this looks like in equilibrium. Yeah, so namely, the number density at high temperatures is just proportional to T cubed for relativistic particles. And for non-relativistic particles, there's a Boltzmann suppression. Actually with a factor of T to the 3/2 here. Yeah, so where does that Boltzmann suppression come from? Well, basically exactly from this factor here. So there's an e to the minus et that is dominant or leading just a mass, and that's exactly the e to the minus m over t that you can pull out of the phase space integral. Okay. So then we can discuss this equation here. So if we plot here, for convenience, not the number density, but the co-moving number density, and here time, yeah, then, okay, so what happens at early times? Recall that A is roughly proportional to T, inversely proportional to T. Yeah, since at early times, yeah, the particles are still relativistic, n goes like T cubed, so this must be a constant. Yeah, so if we now plot NEQ, first of all, this is like this, yeah, and then around the point where they become non-relativistic, there's an exponential suppression. Okay. So then we can see what happens for the dark matter particles. At early times, yeah, this term here on the right-hand side will dominate. Yeah, they're very efficient interactions going on because the number densities are high, even n squared. Yeah, so that means that at early times, the dark matter particles will follow the equilibrium distribution. You can see that from the form of the equation by noting that, well, let's assume that we are slightly above the equilibrium density. Then this will be a slightly positive value, multiplied by a large interaction rate. So there will be a negative sign in front of how the co-moving number density evolves. So if we start here, we'll be pushed downwards. But once we are below the equilibrium line, the argument turns around. So then this one is smaller than this, so this term is negative. With this one, it becomes a positive sign. So we will get a positive correction and will be pushed upwards. So numerically, you will, very quickly converge to the equilibrium value. Okay, so that means that this term here, this is an attractor that forces you to the equilibrium solution, meaning that we will just follow the equilibrium solution until at some point this term here becomes more important. But what happens when this term becomes more important? Well, that is just saying that we can neglect the right-hand side. But neglecting the right-hand side is something that we've already discussed. There's a zero on the right-hand side, meaning that the co-moving number density stays constant. So asymptotically, we know that the evolution must be like this. So the co-moving number density is constant at very early and at very late times, but for completely different physical reasons. Here, because the interactions are very efficient. Here, because there's essentially no interaction going on. Then, you can solve it numerically. Find some smooth transition, obviously. So this happens at the point of freeze out, when, well, these terms are roughly the same. Okay, and that also tells you that, okay, how does the final dark matter density, this is basically, this stays constant until today. So this is the co-moving number density. So in order to get the energy density that we actually measure observationally, the omega dark matter, we just have to multiply by the mass of the dark matter particle. So how does this depend on the cross-section then? Well, if you increase the cross-section, that means that you will stay longer in thermal equilibrium before the Hubble expansion takes over. So that means that you would freeze out later as you increase your interaction rate. So that means there must be a one-to-one correspondence between getting the final dark matter abundance right and the interaction rate in the early universe. Okay, just to mention that this is actually, this kind of freeze-out mechanism is not only important for dark matter production, but also in the standard model. So this is exactly how neutrinos decouple from the thermal bath. Just that neutrinos, they decouple while they are still relativistic. So then, if you decouple at some point here, the final number density does not actually depend very crucially on the point of freeze-out. While if you decouple as a cold relic, so after x equal to 1, for x larger than 1, then final number density depends very crucially on when you decouple. So this is referred to as a cold relic. And this here as the freeze-out temperature. Okay, so when does that happen? Let's first do a rough estimate. So we know that this happens when the number density at freeze-out times the interaction rate is roughly the same as the Hubble rate at freeze-out. Now, just from the cosmology part, you know how to estimate the Hubble rate. Yeah, this is during radiation domination. Yeah, so during radiation domination, the energy density scales like T to the 4th power, which must be equal to the Hubble rate. Yeah, and then you need to get to the dimensions correct, and that's of course the gravitational constant, so a Planck mass. Yeah, so that's Tf squared by m Planck. Okay, and on the other hand, we can also express the number density in a different way. Yeah, we can express it as the energy density at freeze out divided by the dark matter mass. Yeah, but of course, this is a non-relativistic particle, so we know the number density will just redshift away. So the number density at freeze out we can relate to the number density at EQ, at equilibrium, at matter radiation equality. So now the EQ is matter radiation equality, not the equilibrium here. So let's put it like that. Times the redshift factor. Yeah, so times T equality by T freeze out cubed, and of course the other way around. Yeah. Okay, so far we haven't used yet the fact that we should get all of the dark matter that we observe. So how do we use that? Well, these are order of magnitude estimates. So by order of magnitude, saying that we get the right relic abundance means that there should be about as much dark matter as matter in total. Yeah, but equality is defined as the point in time where the radiation component has the same energy density as the matter component. Yeah, so by requiring that this is the same as the radiation density at the time of equality, we satisfy the relic density constraint. Okay, so how do we know, how do we re-express the radiation energy density content? Well, for radiation, that scales like T to the 4th power. So this here we can estimate as just T equality to the 4th power. Yeah, so that means that in total, T equality to the 4th power divided by T equality cubed. So we have T eq left. There are 2 powers Tf squared. I want to write it like this, and a Tf by m. Yeah, this here is order 1 from our picture. Yeah, we should actually freeze out relatively shortly after it becomes non-relativistic, because otherwise we just deplete the dark matter density too much. And then, well, you can combine the two sides of this equation. You can just read off that it doesn't actually depend on the freeze-out temperature anymore explicitly, because you have a Tf squared on both sides. And you can formulate this as a condition on the interaction rate. So that is just the geometric mean of the temperature at equality and the Planck mass. Yeah, you can plug in numbers. T equality is about 0.3 electron volts. Planck mass is 10 to the 19 GeV. So this is roughly 10 to the minus 10 GeV squared. Yeah. Okay, so, but of course you can do this better. Yeah, for example, you can actually solve this equation numerically, taking also into account like the full expressions. Now I've wiped it out, but the full expressions for the energy content that depend on the number of degrees of freedom in the early universe. And then you find something like this. That's a way this is often stated, yeah, in terms of cross-section, in terms of in units of centimeters cubed per second. Yeah, and well, we can re-express this as in particle physics units. which is roughly the same as we just derived order of magnitude wise when you remember that this here should be 0.1, 0.12. So this is actually turns out to be a pretty good estimate. Okay, so what does that mean? Well, the cross section, we can parameterize in general, like if you think of let's say a process like this, two dark matter particles annihilating into photons, for example, you will have two couplings. So the amplitude will be coupling squared, cross-section coupling to the 4, so some effective alpha squared, and then because of the dimensions, it should be a mass squared. So this is 0.1, for example. So note that this only fixes the ratio here. So we don't get the mass scale or the coupling scale independently, only the ratio of the two. So for example, if we choose the mass to be TeV and the coupling order 10 to the minus 1, 10 to the minus 2 or so. So that means that particles of this type here, with masses in the electroweak range and coupling strengths in the electroweak range, actually automatically give the right Rayleigh density, the observed one. So they generically produce the right Rayleigh density. And I mean, this is what you will have heard about. So these are referred to as WIMPs. And well, historically, this is not sure whether you know that. It's not a coincidence that these things were called WIMPs, because the prime candidates for dark matter before this mechanism was discovered were well, basically undetected planets. So very massive objects. And the name for them was massive halo accompanying objects, machos. So this was the opposite of a macho, so we have WIMP dark matter. Okay. Then you've probably also heard that these WIMPs are typically mentioned along with something that is referred to as a WIMP miracle. So let's explore what that is. So this refers to the fact that this is not an arbitrary scale. It's actually a scale that is interesting for a completely independent reason from the point of view of particle physics. So in particular, in the standard model, you have the hierarchy problem. So in a nutshell, you look at diagrams like this, and notice that they are quadratically divergent. And that raises the question, how on earth can the Higgs mass be so light as we have it? Because you would expect contributions from any unknown higher physics. So you basically need to finely tune the counter terms in order to get rid of these divergences. And much of the activity in building theories beyond the standard model has focused on exactly identifying extensions of the standard model to get rid of this problem. And it turns out that all these theories, essentially all of them, contain particles with these characteristics that could be a dark matter particle. So that means that there are really many good candidates candidate BSM theories. So for example, supersymmetry. Yeah, by good, I mean that they were designed not to solve the dark matter problem, but to solve problems like this one. And then they contain dark matter particles that automatically give the right relic density as a byproduct. And this is typically referred to as the miracle. Of course, later, people realized that what I just stressed, that it's actually really only the ratio here, so that already put some doubt on how miraculous this is. The same mechanism would also work for lighter dark matter if you decrease correspondingly the coupling strength. And sometimes these days, these particles, so GeV scale particles or even sub-GeV, are also referred to as WIMPs. But of course, there's definitely nothing miraculous there, because we don't expect any independent things hinting at these scales. Just sort of looking at this kind of physics and saying that, that works as well. Okay, so the other thing, what is so nice about WIMP dark matter is that it's a very predictive scenario. Why is that? Well, we basically just calculated the cross-section that we need to get the right relic density. So that is basically this process, annihilating dark matter into standard model particles. But then, of course, if we know that, we can test this. Today we can, for example, smash together particles in collider experiments, ordinary particles, and produce dark matter. So this is like for collider searches. You could look for, you wouldn't see the dark matter particles in your collider experiments, but what you would see is missing energy, or more precisely, missing transverse energy, which your detectors should pick up. When you reconstruct the energies of all detected particles, something is missing. That would be a signal for invisible, in quotation marks, particles that are produced. In this direction, this goes under the name of indirect searches. So you basically point your telescope or whatever other method you use to regions in the sky and in the galaxy where you have large dark matter densities. Then you would, for example, the galactic center, then you would expect dark matter particles to meet with a relatively high probability. You can calculate the rate of this process because you actually know the matrix element, the size of the probability amplitude. And you can calculate the flux of the particles that you see. And then finally, you can look in this direction, and that goes under the name of direct searches, direct dark matter detection. Where you try to look for dark matter particles elastically scattering on nuclei, or also electrons, but mostly nuclei in this context, in underground detectors. And the whole point is, again, that at least initially, there was this very nice connection plus a very predictive theory. So there has been an immense experimental effort to look, for example, for exactly this kind of mechanism. So, unfortunately, as you know, because you've read the news or not read the news, what used to be a big plus of WIMPs has turned into a problem. We haven't seen any signals, meaning that this whole idea, at least in this very simple form, is just ruled out. It doesn't work. We would have seen these signals. So vanilla WIMP dark matter is ruled out. So what do I mean by vanilla WIMP dark matter? By vanilla WIMP dark matter, I mean exactly things like that. yeah, where you make a strong connection to the WIMP miracle by saying that it should be something at the electroweak scale, yeah, 100 GeV up to TeV maybe, yeah, because otherwise if you push it to even larger scales, I mean, these solutions of the hierarchy problem don't work anymore. The other thing I mean by WIMP, by vanilla here, is that this argument actually works. Yeah, so that there's only one single number that describes all these processes. Okay, but then of course you realize that once you look at actual theories, there are many, many exceptions to this. Yeah, and exceptions in quotation marks again, because they are really very common in these scenarios. So there are two classes of exceptions to this kind of argument. One is that the psi's here that are relevant to set the relic density don't have to be the same psi's, not the same standard model particles that you look for in your detection experiments. Yeah, to give you an extreme example, if dark matter, for whatever reason, would only couple to neutrinos, yeah, with the cross-section that we need, you could produce the correct relic density, but it would be very tough to see it at, say, colliders or in direct searches. Yeah, that would all be loop-induced. So you can easily avoid that conclusion. The other class of ways around, which is also very common, is that we have to remember that what enters here is the thermally average cross-section at a specific time, namely at freeze-out. Yeah, and that doesn't have to be the same as the thermally average cross-section or the average cross-section that you test today. Yeah, so this can be actually much larger than the cross-section today. So why is that? Okay, but before I list some examples or possible exceptions here, any questions?
Sorry, what's RD?
Relic density. Yeah, freeze out. Okay, so then let me just list some exceptions and then we can take a break. So one is, I mean, and typically you, of course, I mean, if you have a contact interaction, you would expect the matrix element to just be a constant. Yeah, so in the non-relativistic limit, this is largely constant as well. But in general, you would expect that you can actually expand this in terms of the relative velocity. And then, well, you can do the velocity average. And of course, a constant should be the same constant, and the velocity dependence here turns into a temperature dependence, and so on. Yeah. So then, well, okay. So maybe let me first mention that there's some conventions related to how you call this expansion. Yeah, these are just the coefficients of the, it's a Fourier series basically in the velocities. Yeah, and sometimes people refer to just this term here as an S wave and this one as a P wave. Yeah, but that's of course not correct. Yeah, because S wave just refers to the fact that you have a, well, S wave as in a partial wave decomposition, so something that doesn't have any angular momentum, and P wave is the next order in the expansion. So the S wave actually has both this term and this term. S wave just means that as you send the velocity to zero, there's a remaining contribution like that. P wave means that as you send the velocity to zero, there's no A, but B is the dominant contribution. Yeah. Okay, this is just a footnote. But why is this relevant here? Because today, in the galactic halo, we can measure, we don't measure dark matter particles, but we can measure the gravitational potential. So we know, as I discussed yesterday, the expected rotational velocity of dark matter particles, or the expected average velocity of the dark matter particles. So that is roughly 10⁻³ Yeah, something like 220 kilometers per second in the Milky Way at the solar radius. But at freeze out, yeah, I said that dark matter should freeze out relativistically, but what does that actually mean? Well, we can estimate this by looking at the expression for the temperature in the non-relativistic case. So that's just 1/3 of the momentum divided by the mass, yeah, for non-relativistic particles. And, well, that is, I mean, the temperature we expressed in terms of this dimensionless parameter x like this. Yeah. Now in practice, I said that x is order unity. It should freeze out relatively soon after it becomes non-relativistic, but the better estimate is maybe around 20 or so. Yeah, in order to get, I mean, you have to revisit this calculation. In order to actually get the correct relic density, you need to freeze out at around this value for TeV masses. This is a statement that depends slightly on the dark matter mass, but only logarithmically. Okay, so then we can turn this around. Yeah, so we divide by mass. So then it's non-relativistic. So P by m is just a velocity. Yeah, so that means that the velocity is should be given like the square root of 3 by 20, roughly, at freeze out. So this is something like 0.4. Yeah, it's not that non-relativistic actually. Yeah, so particles are on average moving rather fast. Okay, but then you can see easily what happens. Like if we have an annihilation rate or a model where the A is absent, this term here will be much, much larger during freeze out than during today's attempts of indirectly detecting the particles, for example. So this one here, you can actually do analytically. Yeah, this is, I mean, I don't have time to go through this, but this is, for example, discussed in Kolb and Turner. There are other exceptions, which you definitely can't do analytically anymore. Where you have a strong velocity dependence that you cannot in any good way express via Taylor expansion. Yeah, so examples include kinematic thresholds. Yeah, imagine that in this case, the relic density is set by a setup where the dark matter particle is actually slightly lighter than the standard model particles. Yeah, then at early times, the energy, the kinetic energy of the dark matter particles is still high enough to produce standard model particles, so dark matter can annihilate into standard model particles, but today it's not accessible kinematically anymore. Yeah, so you completely shut off indirect detection signals. Another example would be resonances. Yeah, you could have a annihilation that is resonantly enhanced, like this. Yeah, and then you could, I mean, if the mediator particle is roughly 2 times the mass of the dark matter particles, then you will be pretty much on the resonance, either during relic density or today, or something in between. But you can basically have both effects. You can have an enhanced annihilation today, putting stronger constraints, or a much larger annihilation rate at early times. And there are also various non-perturbative effects. Going under the name of Sommerfeld enhancement, bound state formation, and so on, that also induce strong velocity dependencies, which you can't solve analytically typically anymore. Another very common possibility is co-annihilations. Yeah, so that is a situation where you do not only have one dark matter particle or one additional state in the dark sector, but you have basically a network of states. With some mass ordering. And then you have a lightest particle. And typically these kind of setups are such, like for example in supersymmetry, that you have a parity. All the new particles, like the supersymmetric particles, are charged under this parity, R parity in supersymmetry. So they cannot directly decay to standard model particles, but they can decay into each other. But of course the lightest of these new particles is then absolutely stable. Yeah, so what will happen then is that there's a network of Boltzmann equations where you produce all these particles. Yeah, they cannot decay into standard model particles, but they will eventually decay into the lightest particle. Yeah, and it turns out that you can, what sounds like terribly complicated, you can actually reformulate this network of Boltzmann equations into a simple equation for the sum of all the dark matter particles, all these additional particles. Yeah, because all these particles will eventually just decay into the latest one, so that is actually the dark matter density that you will observe. And when you do that, you end up with an effective Boltzmann equation that looks exactly like the one that we've seen, but just that the sigma v that is there is an effective sigma v that effectively sums over all annihilation rates. Yeah, and that is another way of how to achieve this one, because today annihilation, these heavier states are not around anymore, but they contribute to an effectively enhanced annihilation rate at early times. Yet another very well motivated option is to have asymmetric dark matter. Yeah, you could have both dark matter and anti-dark matter particles. And asymmetric just means that, they don't have to come with the same number densities. This would, in some sense, correspond to a different, production mechanism, but it's motivated by the fact that, we know very little about dark matter, but the one thing we know is that the number density or the energy density today is very similar to that of ordinary matter. And ordinary matter, the abundance that we see is of course not given by the freeze-out mechanism. It's given by some primordial asymmetry. That we only have, the universe is basically only matter, not antimatter. It's not set by the thermal equilibrium density of a symmetric component, but just by the asymmetric component. Meaning that the interactions in the standard model are much, much stronger than what we need in order to get dark matter in the WIMP paradigm. Basically all the symmetric parts have annihilated away in the early universe, and we're only left with the asymmetric part. So that would mean that applied to the dark matter case, we've only one of these species left. It's of course a matter of convention of which one we call which. And then if these are not around anymore, only those, there cannot be any annihilations. So this one would even be strictly zero today. Okay, and then, there are many options. Just one I want to mention is that we could have also the same freeze-out idea, just the psi doesn't actually have to be a standard model particle. There could be a completely secluded dark sector, dark radiation, sterile neutrinos, for example, and the same story would work. In some sense, this is, a combination of both of these. So the point is that for all of these here, like not for one, but for 2, 3, 4, 5, and other well-motivated scenarios, you basically have to resort to numerical methods. And there are a number of public tools available to do high precision calculations of the relic density, basically for all of these cases. So like Daxusi, Micromicus, MATDM. Yeah, and one of the exercises is exactly intended to introduce you to one of them, because then you can also ask me about details. So this is something that I put at the bottom of the exercise just to get started and installed the package such that we can look at some applications like maybe on Thursday or so. Okay, that's time for a break. Any questions? Or we take the break first and then the questions. Is this on again?
Doesn't sound like.
Is this on?
Yes.
Okay.
Muted.
No,
but
she says it's on. It's on, right? Is it on?
No, this is on, but the other one.
Ah, the other one. Ah, this one is muted. Ah, I see. Okay. Ah. It's complicated. Okay, so let's start with questions. Any questions about the freeze-out part? Or any further questions? We had quite a few questions during the break already. Yeah. Relativistic freeze-out. Yeah, very good. Now I just wiped it out. So I mentioned this briefly. I mean, freeze-out is actually implemented in the standard model for neutrinos. So it's exactly this picture. You have a Boltzmann equation like that. You freeze out before the particles become non-relativistic. Yeah, relativistic freeze-out means that the final abundance is very insensitive on when exactly you freeze out. Now, of course, you can also freeze out at the transition, like x about 1, m about t. Yeah, but then from the dark matter point of view, there's a constraint from structure formation. So we estimated that for very cold dark matter, so late freeze out, x20 or so, the velocity is 0.4. Yeah, if you freeze out earlier, the velocity at freeze out is larger. Yeah, so that means if the dark matter particles move too fast, structure formation will not be as efficient. Concretely, if you have like small regions that are slightly overdense, a little bit more dark matter than here, yeah, from my general arguments, you want them to collapse, form significant gravitational potentials. Now, if in this small overdense region the dark matter particles are moving too fast, they will stream out of these overdense regions, such that these overdense regions actually don't collapse. Yeah, and that's something that you can test. I mean, basically, like the easiest thing is just to point to the very existence of dwarf galaxies. Yeah, that's the smallest scale that should have become nonlinear by today. Yeah.
Does this rule out then relativistic freeze-out?
Yes. So, I mean, like you can translate that to a mass when dark matter particles could have frozen out. Yeah, and if you have a particle like this, like I sketched here, that is lighter than a keV, roughly, then it is too light. It would have frozen out too relativistic in order to give the right relic density. Yeah, but particles that have been in equilibrium at early times, that are heavier than a keV, for those you can have this freeze-out mechanism to work. Yeah, thanks for the question. Other questions? Okay, so then let me add something. So I assume that this kind of freeze-out mechanism is something that many of you will have seen. Yeah, so now I will add an aspect that I guess people are less familiar with, and that goes under the name of kinetic decoupling. Yeah, so I mentioned one important assumption in deriving the standard form of the Boltzmann equation, namely that we are in kinetic equilibrium. Yeah, so remember that we have interactions like this. Dark matter particles annihilating into heat bath particles. Yeah, and then this as long as it's in equilibrium, it establishes chemical equilibrium until freeze out, which happens around x of 20. And the observable that you connect to this freeze out process is the dark matter density. Yeah, because you constantly change the number density in the process. Okay. So why did that work? Why could we assume kinetic equilibrium of the dark matter particles? Because if you turn around the diagram, then like naively I would say that the amplitude for these two processes must be the same, but the rate is still grossly different. Why is that? Because these are already non-relativistic particles, so they are Boltzmann suppressed in their number densities, while these are relativistic particles, they are unsuppressed. Yeah, so if we turn it around, we suddenly have a particle with a large number density in the initial state. So the rate of this one must typically be much, much larger than this one. So during the entire freeze-out process, these processes will always be like very, very frequent, establishing kinetic equilibrium. But of course, at some point, also these processes will become irrelevant, because the Hubble rate takes over. Due to the expansion of the universe, there will be so few dark matter particles that this is not efficient anymore. And then we can introduce a kinetic decoupling temperature, which generically is much smaller than the freeze-out temperature, the chemical decoupling temperature. So, what is the observable related to this process? Well, this gives you a cutoff, a small-scale cutoff in the power spectrum of matter density perturbations. Now, you can think of this as the smallest gravitationally bound objects that can form, the smallest protohalos. So why is that? Well, there are two independent effects. One is that while these scatterings are still efficient, density perturbations cannot grow. You will learn in Yvonne's lectures that during radiation domination, even if you have an overdensity in the radiation component at some point, like locally, it will just freely stream out. So this overdensity cannot grow. So that means that even if dark matter would, in quotation, want to cluster, it scatters all the time with the heat bath background, which washes out the density perturbations. So, no growth of density perturbations. It's a question of scale, so basically how far information can propagate, these scatterings. So this is then smaller than the sound horizon. It's the same physics as you will discuss for the CMB. So this is the sound speed. In principle, this leads also to the same oscillation pattern that we see in the CMB. That's just that it's unfortunately much more difficult to directly observe the power spectrum of the dark matter component alone. But then there's another effect that right after kinetic decoupling, due to these scatterings, the dark matter particles still have a residual velocity, because they inherit this temperature, and that leads to a free streaming effect. So they will freely stream out of the overdense regions, and this free streaming must not happen on too large length scales, because otherwise you would also erase structure on these scales. So we have a washout of density perturbations on scales lambda smaller than the free streaming length after kinetic decoupling. And this is efficient basically until equality, when matter domination takes over. Yeah, so here it's the average velocity of the dark matter particles after kinetic decoupling that enters. Okay, so how do we describe kinetic decoupling then? Yeah, we learned how to describe chemical decoupling by starting from the Boltzmann equation and considering the leading moment. So now we want to discuss kinetic decoupling. And it turns out you can do exactly the same thing, you just have to go to one higher moment of the Boltzmann equation. So in particular, it's sufficient to consider, well, the second moment, you can call it velocity dispersion, but it's much more intuitive to call it a temperature. Yeah, as long as you remember that this is not actually a temperature, but just a parameter. So it has the meaning of a temperature in equilibrium, in kinetic equilibrium, but you can define it even afterwards. Okay. So I define this temperature T, or the parameter T, in this way. Yeah, so what do I mean by this average? Just the average over the phase-space distribution. Yeah, and then you quickly realize that, well, if you use a thermal distribution here, then this average gives you exactly the temperature. Yeah, that's of course why I use this convention. So this is the heat bath temperature for temperatures much larger than the time of kinetic decoupling. On the other hand, for temperatures much smaller, yeah, so at much later times when these processes are no longer efficient, what do we expect? Yeah, then there's no interaction, so the way this should be affected is only due to redshift. Yeah, there's the energy, this is highly non-relativistic, so this is just the mass essentially. Then we have the momentum squared, the momentum redshifts, so that means that this parameter should redshift like a squared. Yeah, so not like a, like 1 over a in equilibrium, but like a squared, a to the minus 2. So some constant divided by a squared. Yeah, in practice, when you solve the Boltzmann equation, the transition between these two regimes is actually very quick, which you can use to define this point of kinetic decoupling. Okay, so how do we do this in practice then? We can again look at the Boltzmann equation, and instead of the leading, yes?
What is the G in this equation?
The G is the number of degrees of freedom, internal degrees of freedom, yeah. And the N is the number density, right? So this is just the standard definition of a thermal average, yeah. Okay. So, just as we defined at Cn as the leading moment of the phase-space distribution, we can now define the next moment, T for temperature, of the Boltzmann equation. Yeah, so we can define it as, well, taking the momentum average like this would be the number density. Now we add a factor like this, p squared over 3. And this should then be the same, well, following the Boltzmann equation, the collision term should be the same as the Liouville operator. And, well, remember that the Liouville operator, once you divide by, okay, so L over E is dt minus h p pf, like this. Yeah, so then we multiply this with p squared over 3e. The first term, yeah, that will give us the same as before. We can just pull it outside the integral. Yeah, so we have a dt acting on the phase space integral of all of this, but the phase space integral of all of this is just our definition of t times n. Yeah, so this is n times t chi. Yeah, and then the next term, we have a minus h, and then a g e3p 2 pi cubed 1 over e. So we have a p like this, and the p, this acts on a p squared over 3e. Sorry, it's the other way around. Yeah, like this. Well, this we can again solve by partial integration. So this gives a minus, and then we have the derivative acting on this term here. Yeah, so let's maybe write it in components. That's always easier. So we have a d pi and then a p squared over 3e. Yeah, the e is roughly just an m, yeah, because we're non-relativistic. So then we have to take the derivative with respect to these. Yeah, so that is, acting on this one gives a factor of 3. Acting on this one gives a factor of 2. So in total we get a minus 5 p squared over 3e. Okay. So that means that well, we can reorganize this a bit. These terms, yeah, I factor out an overall factor of n. Then from the first time derivative, yeah, I get a time derivative on the t chi plus, and then the time derivative acting on the n. So t chi n dot over n. And then you see that, well, if we have this term here inside the integral, what remains is again just the definition of this temperature parameter. Yeah, so here again we have the temperature parameter. So plus 5 h t chi. Yeah, plus, and now I neglected higher orders. Okay, this one I can further simplify. Yeah, because the n dot I know from my lowest moment of the Boltzmann equation. Yeah, I follow this hierarchy here, so I assume that freeze out has already happened, meaning that the number density of the dark matter particle stays constant. But then of course I can use the Boltzmann equation to write this as minus 3. Yeah, so if n dot, no, if the number density doesn't change anymore, effectively. Yeah, so this is the form of the Liouville operator. I can also calculate this first line here, starting from the full expression for the collision integral, which takes a very similar form as for the annihilation part. Just now you actually have to be careful. I mean, I will put this in my notes, that you have to include the quantum mechanical factors here. Well, you didn't need to do that in the case of WIMP annihilation, which is something that you explore in the exercises. But here you need to take into account that these standard model particles, the heat bath particles, the relativistic particles, can have very high occupation numbers. So we need to take the final state quantum mechanical corrections into account. So you need to take that into account, and then you can basically use an expansion using a kinematic argument that these are very light particles, these are heavy particles, non-relativistic particles. So you have a separation of scales, which means that in a given interaction, the momentum that is exchanged is always small. So you can expand in this parameter, just as you expand in the temperature over m. And well, we also use that the temperature is smaller than m. And then we arrive at the following form. That this is 3/2 times the function gamma, which I will explain in a moment, of this form. So n is the number density. So that means in total that our Boltzmann equation, or the next moment of the Boltzmann equation, takes this form. Okay, so this gamma here is the momentum exchange rate. And this is roughly given by the scattering rate times a factor of t over m. So there's a suppression of what you would naively expect, and the reason is that like on average, like assume that you depart from a kinetic equilibrium. On average, it's not sufficient to have a single scattering event in order to restore a thermal distribution, a Maxwellian velocity distribution. So rather what is happening is that the particles, the dark matter particles, perform a random walk in momentum space. So you add an additional diffusion scale here. You need a certain number of scattering events before you can restore kinetic equilibrium. Okay, but once you identify the correct rate here, you see that it's very similar in the form of the Boltzmann equation for the number density. It's an attractor equation. So as long as this rate here is much larger than the Hubble rate, we have an attractor to the equilibrium state. T chi should be the same as T. We are always driven to that equilibrium solution. While, on the other hand, once the Hubble rate takes over, we have a 0 on the right-hand side. And then you can solve this and see that we get exactly the redshifting that we would have expected. That T chi scales like 1 over a squared. Okay, so then I said that this is related to the cutoff scale. So what does that mean concretely? So from solving this equation here, you can get the kinetic decoupling temperature, and from that the cutoff scale. But this is model dependent. So just as the relative density is of course model dependent, just that we have a measurement, it's much harder to measure the cutoff scale. So in this scattering rate here, or the momentum exchange rate, of course the matrix element for the elastic scatterings enter. So that's where the model dependence comes from. So this is roughly 10 to the minus 11 to 10 to the minus 3 solar masses for neutralinos, neutralino dark matter, which you can take as a proxy for standard WIMPs. So this is very small, and there's no obvious way of how you would observe this directly. You sometimes still hear or see in the literature that people claim that the cutoff due to this effect is Earth mass. Earth mass would be 10 to the minus 6 solar masses. But that is based on a misconception in the literature, where this calculation was done for a very specific case, namely 100 GeV Beano dark matter. So already for simple WIMP models, there's a large range. Now, if you extend your model class, you can also prolong kinetic equilibrium until very late times. You can have very late kinetic decoupling, and you can get all the way up to the scale of dwarf galaxies, in principle. So I'm just listing 2 examples of model classes. So for example, if you have TeV dark matter with MEV mediators, so essentially long-range interactions. So you have dark matter particles annihilating into light new mediators like that. That would set the relic density, and then the scattering is via the same mediators to standard model particles. That gives you a very late kinetic decoupling. Or if you simply have KeV, namely warm dark matter, then you also have very late kinetic decoupling, very large cutoff scale, and then you have immediate observational consequences. So you can use, well, in the simplest way, the fact that we observe dwarf galaxies to constrain these kind of theories. But you, like in a more sophisticated way, you can see this as an imprint in the powers and in the Lyman alpha spectra, for example, that I think Yvonne will discuss. Okay, that's what I wanted to say today. Any questions? Yeah. Yeah, so relativistic particles, yes, it's discussed in the context of neutrinos, not the least, but it's much more complicated because of this. So actually performing this calculation is greatly simplified due to this separation of scales. Even in that case, it's at the level where I would not want to put this as an exercise. So it's much more complicated than the corresponding case for the number density. And without that, if you can't use that, it's much harder to solve all the integrals in the collision integral. So you have to largely do it numerically. Any other questions? Yeah.
Sorry, I think I missed the physical meaning of this cutoff mass. It has to do with structure formation.
Yes. So it has to do with structure formation. I told you in the beginning that dark matter is basically needed in order to explain the inhomogeneities. So we need small perturbations. That's what Yvonne started to discuss today. And we need dark matter in order to understand how these initial tiny perturbations grew so large that we actually can observe any structures today. Okay, but that means that there must be some initial density perturbations in the dark matter fluid, which then grew large, at least at all the scales that we can observe. Now, as long as these processes are very efficient, even if you start out with some initial density contrast in the dark matter fluid, for example, produced by inflation, they will be washed out. So there won't be any structure at these scales. And that is how, it's only after these processes cease, so this corresponds to a scale, so basically the horizon scale at that temperature. And only at scales larger than this scale, you can expect any structures at all. So this presents a lower cutoff in the power spectrum of matter density perturbations. Yeah, there cannot be any gravitationally bound systems below that scale. Yeah. Okay, I'm also around the entire afternoon, so don't hesitate. Yeah.